record it down for you. Okay, let us make a start. This is your syllabus. Right? Always refer to your syllabus so that you know what are required, and then do past year paper to make sure that the syllabus is covered. Right? Because it's always difficult to interpret the syllabus. Only by doing the past year paper, then you know how fully the examiner require of the syllabus. Okay, remember all this for this part. Right? This is a okay.
Yeah.
This is the atomic. This is the, if you like, the average mass of a proton and neutron in a nucleus. So usually they will ask you to calculate the mass of, let's say, iron, and then you have to use the mass number times this number. Okay.
Okay.
Rest mass of neutron don't give. Proton, yes. And then rest mass of electron. Okay. Other than that, no formula given. Right. So important to know what is given, what is not given. And then this value, you can think it of 1 joule equals to 1 electron volt. This one,
Okay.
give you electron volt. Okay. Let's worry about all those things there. Okay. First thing you need to know is Geiger-Müller scattering experiment. Right? That's your source of alpha material. This is your
Okay.
sulfide screen. The idea is if the alpha hit the screen, you'll see a scintillation, a tiny spark. And then this is your gold foil. Experiment is done in an evacuator vessel. Why? Why is done in evacuator vessel?
So that the alpha particles don't hit air, don't collide with air molecules.
Okay, good.
Yeah.
Because you don't want the air particles to disturb the experiment. Air particle, when the alpha collide with the alpha particle, it will be deflected. Right? It won't go into its own direction. So evacuator is in a sense like vacuum already lah, no air. And then that is how we can explain it. This is the angle, this direct line there, incident particle, that's direct there.
Yeah.
And then the angle is this angle. Right? The deflected particle made with the incident direction. Alpha particle are directed at the target gold foil. Right? It's thin. Usually we want it as thin as possible. So there is not many layers. We just want multiple scattering. As long as it hits one atom, good enough. So that's why it's thin. Thin so that it's close to a few layers of gold atom. Do not want multiple collision. That's your zinc sulfide. That's your alpha particle are deflected. Right? It's our various angle. And this is the angle. That's how we measure it. That's this is your evacuated chamber. It's actually a vacuum. And then there's your cavity. There's your aluminum source. Aluminum will give you your alpha particle. Lead cavity because we don't want it to go anywhere. We just want it to come out straight. There's your gold foil. There's your, we call it scattering angle. And then the fluorescent zinc sulfide screen. The idea is where the alpha hit it, you see a tiny spark there. We call it scintillation. Microscope. So the people, the scientists there must be very patient. Sit there for hours counting the scintillation. Okay, what is an alpha particle?
It's a helium, I think.
What?
A helium nucleus.
Good. Not helium atom, helium nucleus. So He2 plus. What's the aim of the Geiger-Mason alpha scattering experiment?
To prove the what is called this, like it's the Rutherford model, right? I think so.
You want to study the atomic structure. That means how is the atom built up? Atomic structure, keep that in mind, atomic structure.
Okay.
You allow the size of the nucleus of the target to be estimated also. I remember, not nuclear structure. We don't know about anything about the nucleus. We only want the atom. How is the atom built out of? Not nuclear structure. Examiner will want to catch you sometimes. Right? Tell us nothing about the nucleus. It just tells us that the nucleus is positively charged. Doesn't tell us that the nucleus has a neutron and proton. Okay, we won't bother about all these. Function of zinc sulfide. Right? Scintillations, or we call it tiny spark or pinpoint of light, are seen where alpha particles touch the screen. The scintillation can be observed using microscope. Okay, so that's your incident direction. We see most of it. Most pass through without deflection, and the angle is measured from the incident direction. That's the scattering angle. Some, we call it some alpha particle, or 1 in 1,800 are deflected through small angle. Few, this one is few, right? Remember, this is our direction. More than 90 degrees is behind already. 90 degrees is here. Right? Few are deflected to an angle greater than 90 degrees. We can use, we can measure it with different angle, right? The alpha particles plotted against graph. So we will see something like exponential lah. Here will be the incident direction. Right? More than 90 degrees become less and less. Don't worry about this theoretical and Rutherford formula. There's you have to have experiment result, and then you have to have theoretical calculation to show that it is true. So we are not worried about that. Stop me if I'm going too fast.
Okay. I'm fine with it.
Okay, so if it's solid like that, if the atom is solid like that, then the alpha will be just deflected like that lah. Won't go through. Right? We will not see normal atoms repulse at 180 degrees if it's directly hitting that 180 degrees. Or angle, if it's at an angle, then angle of incident equal angle of reflection lah. Most alpha particles are undeflected, implying that the nucleus occupied tiny volume of the atom. Right? Nucleus compared to the atom is very tiny. So there are a lot of empty space between the one nucleus and another nucleus. Okay, so we can see the path there. These are the different paths. Most pass through undeflected. Direct collision will be rare. That's why we see deflected backwards there. Direct collision, this one, direct collision will be deflected backwards. If it's at an angle, then it's deflected at an angle. Right? Others will be quite near the nucleus. A few alpha particles are slightly deflected. The nucleus is positively charged. Right? If it doesn't charge, it will go straight through. But because it's positive charge, there's a repulsive force there. If the nucleus is uncharged, the particle will shoot straight through. Repulsive force between two positive charge. Remember, alpha is positively charged, nucleus is positively charged. Obey the inverse square law. This is your A2 work. That's the closer the positive charge, the greater or the larger the deflection. This explains the deflection at different angle. Right? This is your A2 work. Right? We don't need to know about AS. A few By right, it should be not a few, it should be some. Sorry, I think this one should be, let me just do a correction. The term should be clear, because sometimes it has come out in the exam. This one should be some, not few. Okay, there should be some. This one is few, correct? Right? More than 90 degrees or head-on collision will be some. Alpha particles rebound from the foil must have been moving towards the nucleus. Direct collision. Okay, you are supposed to be able to draw alpha particle path is very far away from the influence of nucleus. Particle that is near the nucleus. Particle is approaching nucleus head-on. Right? A is very far. These two are quite close. This one is closer. This one is direct hitting. So you should be able to draw that. Right? Remember, it's positively charged. Alpha is also positive charged, so there is a repulsive force. That's why it's going this way. If it's nearer, the repulsive force is greater. That's why it equals greater curve. If it's further away, it goes straight through. No influence. The repulsive force is very negligible. If it's direct, then it will be rebounds. Explain whether the electron of the gold atoms affect the path of the alpha particle. Does it affect?
I don't think so. No.
Think of your alpha particle like elephant, and you are the electron. What will happen when the elephant is running very fast towards you? Okay, that is roughly the picture. Alpha particle is about 4 atomic mass unit. Electron is about 1/2000. You can see very, very small. So when the alpha hit the electron, it will fly off. So you're right. It's just like this heavy truck knocking at a small car there, the car will fly off. Electrons are very small mass compared with alpha particle. On collision, they are easily scattered by the alpha particle. The path of alpha particle is not affected at all. It just goes straight through. What can we learn from the experiment? We've done that. Size. Allow the size of the nucleus of the target to be estimated. You can notice it's very tiny compared to the atom. Structure. Allow structure of an atom to be built. Nucleus is positively charged. The electrons are outside the nucleus. Nucleus. It gives us nothing about the structure of the nucleus. That means it tells us the nucleus is positively charged. It doesn't tell us that the nucleus got proton and neutron. Okay, so how to estimate the size? This is just for your info. Rather than memorize it, we can imagine that there's the size of the nucleus, there's the size of the nucleus, and then the size of the nucleus occupied between the two of them. And we can roughly estimate the probability of hitting will be size of nucleus over size of atom. So it's 1 in 8,000. That's why we observe. Then if we know the size of atom, we can calculate the size of the nucleus. Okay, Don't worry about it. Just memorize it, that it gives us the size of the atom.
I see.
That's all. Right? Allow the size of the nucleus, size of the nucleus of the target to be estimated. Compare with the atom lah. We use probability to calculate lah.
Okay.
Rutherford model of atom, structure of atom. We call it nuclear model of the atom. All atoms positively charged is concentrated in a relatively small volume called a nucleus. Right? So the positive charge is concentrated in the nucleus, very small volume compared to the atom. Most of the atom's mass is concentrated in the nucleus. Electrons surround the nucleus at relatively large distance. This one is an estimate size, which you have to do. What is the nucleus of an atom? You are supposed to be able to tell me. What's the nucleus?
It's like the central part of the atom where the neutrons and protons are located.
Okay, good. Nucleus is a tiny but massive center part of an atom. It contains a proton and neutron. What is the size of an atom?
10 to the power negative 10.
Okay, meter. Nucleus?
Wait. 1.25 times 10 to the power 14.
About there lah.
So, times 10 to the power negative 14.
Negative 14 meter.
Yeah.
Okay, good. Yeah,
Yeah.
right. Quite ready. At proton. Proton is positively charged particle found in the nucleus. It's the nucleus of the smallest atom, hydrogen. Neutron has no charge and is found in the nucleus. It's about the same size, same mass as the proton. Right? Remember that the alpha scattering experiment just tells us nothing about what's inside the nucleus. Tells us that it's positively charged. What's a nucleon? Particle in the nucleus. Anything in the nucleus, we call it a nucleon. Can be a proton, can be a neutron. Okay, what is the charge of a proton?
1, I think 1e.
Okay.
Plus 1e.
How about neutron?
0.
Okay. If the relative mass of electron is 1, how about proton? Just give an estimate. Don't need to give actual answer.
2000, I think. 2000.
Okay, about 1 over 2000. Sorry, if you compare with electron, it's about 2000.
Yeah.
Neutron is still about 2000. Don't need to know that exact value. Unless you ask for it. Then this one you can calculate. Don't need to memorize.
Okay.
Mass of proton is approximately the same as neutron. This one you must know roughly. Mass of proton is about 2000 times larger than mass of electron. Right? Representing the nucleus is the chemical symbol X. This is your, either you call it mass number or nucleon number. This is the atomic number Z or proton number. Right? Some people prefer to write this way, but A level we write the other side. Mass or nucleon number is the total mass of nucleon in the nucleus. Major characteristic of an atom is the atomic number. That means it tell us the difference between one atom and another atom. That's a Z, which is defined as the number of proton. And nucleon number is the number of neutron in the nucleus of the atom. So A equals to N plus Z. Okay, so chemical properties of the atom are determined by the atomic number. Number of proton in the atom is constant, and different atom has different number of proton. In neutral atom, number of proton equals to number of electron. Okay, atomic mass unit is based on your carbon-12 scale. There are 6 proton and 6 neutron. Sample of pure carbon are much more easier to obtain than pure hydrogen. That's the reason why we choose it as a standard. Unit is used to measure mass of protons, neutron, and electron because their mass is so small. So it's better to work with things like 1, 2, 3 or 1.4, 1.5 rather than always 10 to the power minus 14 and 10 power minus 15. That's the reason why we introduced another unit. Is the average mass of proton and neutron in a nucleus. That's the meaning of atomic mass unit. Okay, how do we get that? Atomic mass unit definition is 1/12 of the mass of an atom of carbon-12. So 12 grams of carbon-12 has 1.06 times 10 to the power 23 atom. So we can calculate the mass of one atom. Okay, change it to kilogram, divide by the number of atoms, get it as that value. Then since there are 12 nucleons in the nucleus, we divide this by 2. And that's our value. That's how we get atomic mass unit. Atomic mass unit is actually the average mass of a nucleon. That means it can be a proton or neutron. It's in the carbon atom. Isotopes. Isotopes have identical. Atoms have the same atomic number, same Z, but different number of different atomic masses are called isotope. That means they have different mass number. Isotopes are identical in chemical properties, yet they are different physically. Their mass is different. Right? This is the isotope of hydrogen. This has 1 proton. This has 1 proton and 2 neutron.
Yeah.
This deuterium, 1 proton, 1 neutron. For example, there are 3 isotopes of hydrogen. 2 of the isotopes are stable. These 2. Not radioactive, let me say it's stable. But tritium has 1 proton and 2 neutron is unstable. Means it's radioactive. Most elements have stable isotopes. Radioactive isotope can also be created for many elements. That's man-made one. Doesn't exist naturally.
Okay.
So these are various atoms with their isotopes. Isotopes of carbon, there's 12 and there's 14. 6 is still the same. That is always the same. Total number of nucleons, protons, and neutrons in an atom is the atomic mass number. We usually denote by A. Okay, so that summarizes for you what we have just learned. This one you can find in your data sheet. This one also. Neutron has that mass, but it's not given in data sheet, but you must know that it has 0 charge. And that's how we represent the nucleus. Let's go to nuclear processes. Nuclear processes occur whenever the nucleus, when the number of neutrons or proton or both in the nucleus are changed. Right? Whenever the mass number of the nucleus is changed. Nuclear process, yeah, example, fission, fusion, radioactivity, nuclear reaction, artificial radioactivity. In nuclear physics, a nuclear reaction is a process in which two atomic nuclei or nuclear particle collide to produce product different from the initial particle. Right? Two or more collide. Example will be you got your alpha particle here. You bombard your nitrogen with alpha particle. So that is your product, oxygen. And then the other product will be your proton. In principle, the nuclear reaction can involve the collision of more than two nuclei or subatomic particle. It can be more than two, doesn't have to be two. But usually, because all of them are very small, it's unlikely you have more than two. But the probability of three or more particles colliding at the same time is extremely small. And such an exceptionally rare. Okay, how to write a nuclear equation? Okay, there's a nuclear equation. X, Y, give you W, V. Conservation of nuclear number, total mass number is constant before and after the reaction. That means A plus B must be equal to C plus 0. Conservation of charge. Total charge is constant. That means total charge before the reaction is equal to after the reaction. That means you add the bottom one, N plus P is Q plus R. Okay, this one you have to memorize. Okay, we have to stop in 10 minutes time. In nuclear reaction, nuclear number is conserved, charge is conserved, mass energy is conserved, momentum is conserved. Right? Don't need to worry about all this. This is just for your information. So I go very fast. Right? For your information as well. Radioactivity. Right? It doesn't involve a collision. It's unstable. It's the result of decay or disintegration of unstable nucleus. Right? The unstable nucleus we call the parent. It's unstable. And then the product alpha is called the daughter. This is called the daughter. Alpha is the emitter particle. By the emission of a particle or particles, and sometimes accompanied by emission of gamma rays to form usually a more stable nucleus. It's unstable. This one is usually stable, but not necessarily. Sometimes it can be still unstable and then will decay further down. And that's the symbol. If you go to university, they will have a symbol there telling you, careful, radioactive source stored in the lab. Radioactive decay of nucleus is essentially independent of environment of the nuclei. That means it can be an atom or it can be a chemical. right? It can be cold, it can be hot, it doesn't affect the radioactivity.
I see.
Parent and daughter nuclei are different elements. Right? You need to know roughly a little bit only how to write the nuclear equation as well. You don't need to know too detailed. That one is in your A2.
Oh, okay. I see.
Decay, disintegration, transmutation, there's a term used. Yeah, just a brief understanding. Spontaneous and random. Right? That's what it means by spontaneous, independent of its environment. Okay, let's go to, let me see how much time we still have. We still got a bit of time. Let's try asking some question.
Okay.
Sorry. What's the rest mass of proton? Make sure you know how to
Uh,
data sheet.
1.67 times 10 to the power of negative
Okay,
27.
this is just to make sure you know how to find from your formula sheet. Charge of
Okay.
proton?
1.60 times 10 to the power of negative 19.
That's all. The same as electron, except no negative charge as well.
Mhm.
An electron is a negatively charged particle of atom found in the electron cloud. What is the rest mass?
1 9.11 times 10 to the power of negative
Okay, it's
31.
just to make sure you know where to find your answer.
Yeah.
Charge,
Negative 1.60 times 10 to the power of negative 19.
okay.
Cool.
Neutron has no charge and is found in the nucleus. What's the rest mass of neutron?
1.67 times 10 to the power of negative 23.
If they try to be funny with you, then you just give an estimate. It's not given.
Okay.
Okay, I think we won't bother about all that. We have gone over that. What does A represent?
Atomic number.
Right? Atomic number or mass number, number of proton and neutron in the nucleus. Z represent?
Uh, I think Z represents the proton number.
Okay,
Wait, no,
proton
not.
number or number of proton. State the number of neutron in the nucleus.
Uh,
Just one A minus Z, that's
A.
all. Since they're given A and Z. Okay, it's still an unfair question. It's not written down properly. Okay, state the number of proton, neutron, electron in the aluminum.
13 protons, 13 electrons, 14 neutrons.
Good. Give an isotope of aluminum.
Aluminium, 27.
37 given you already, so give another
Oh,
example.
uh, Aluminium, 28.
28. Right? Can be 28, 26, 13 must always be there.
Hmm.
What is the mass of the atom of aluminum? Then call this one. How to calculate?
Oh, uh, 27, 27 U. So,
Then you go and look at U from the data sheet and calculate the mass
yeah,
of kilogram.
yeah. Okay.
Okay, you cannot drive 14 here. Okay, I think this one you know already, so you won't bother. I think we will stop for 5 minutes.
Okay, sure.
Okay, we'll stop for 5 minutes.